Okay, and we are off again doing a few just little clean up topics on states of matter and solutions. And we were just talking about the gas laws ones. Whoops, sorry about that. And now we're getting into some more colligative properties of solutions. Now, the first one we're going to talk about is Raoult's law with a solid solute. Okay, we're going to talk about liquids later. We're talking about a solvent with a non-volatile solute. It will always decrease. Now, this isn't going to be true in a minute when we see volatile solutes, but if we have a non-volatile solute, it's always a vapor pressure depression when it's non-volatile. And what Raoult said is that the vapor pressure, the pressure of the vapor above the liquid, is going to be equal to the mole fraction, be very careful here, of the solvent, not the mole fraction of the solute. That's a little unusual, I think, times the original partial pressure of the solvent. Now, this diagram here represents something I've seen in books. I've seen it in AP question. So I tried it. I set this up under the dome on my vacuum pump, and I marked my liquid levels so that they were even, and I left it there. No kidding, kiddos. It was over a year, and I didn't see this happen. So let's call this a theoretical or a thought experiment until somebody shows me otherwise. Maybe if I'd pulled a vacuum on it, but then it would have pulled the vapor out, so that wouldn't have worked unless I'd pulled a vacuum and then sealed it. I'm not sure how they're doing this. I'm assuming had I been able to pull a vacuum and then just left it, sealed it and left it, maybe it would have worked. But here's what happens. It's this continual push of vapor from one beaker to the other. And that's because the vapor pressure above pure water is going to be greater than the vapor pressure above the solution. So it's a cycle of I increase my vapor pressure of the water, and then that's going to cause this vapor pressure to be too high. So that's going to cause water to condense into the solution. And what that will do then is decrease the vapor pressure of the water above. And so then that's going to cause water to vaporize, which will increase the vapor pressure of the water above, which will make the vapor pressure too high above the solution. So it's going to cause that to condense. Well, that's going to make the vapor pressure too low. So it's going to cause that to evaporate, and hopefully you get an idea. And so in theory, all of the pure water would end up into the aqueous solution over time. And I've seen it. I've tried to prove it. No luck. So let's move on to another example of this. I have ethylene glycol, and it's dissolved in, so we know that this is our solute, 1.5 kilograms of water. So remember, Raoult's law tells me that my vapor pressure above my solution is my mole fraction, be careful here, of the solvent times the partial pressure of the pure. So I have to get to the mole fraction. You have seen this. It showed up on a test and you weren't really happy about it because you totally forgot about it. It's on your formula chart. I need my moles of water and I need my moles of ethylene glycol. And so this is 1,500 grams times 1 mole per 18.02 grams. And that gives me 83.24 moles. Please double check all my algebra here. Moles of water, that's one way I know you're paying attention, is when you bring to me my mistakes. If you bring them to my attention, I know that you are trying these problems yourself. 62.08 grams. I should intentionally put some math mistakes in here as kind of a test for who's paying attention and who's half asleep or doing Facebook while they're watching the videos. Okay, so those are my 2 moles. Now I need my mole fraction of my water. A fraction is a part over the whole. And we just don't multiply by 100 because it's the mole fraction. It's out of 1, not out of 100. And hopefully you realize it's going to be greater typically than 0.55 because the solvent is typically present in the greatest amount. So that's my mole fraction of my water. So now I can calculate the partial pressure of my solution is equal to my mole fraction of water, 0.888, times the partial pressure of pure water, which is 525.8 millimeters of mercury at this temperature. Right, as you increase temperature, you increase the vapor pressure. So it's very important, right? More molecules have enough energy to escape into the vapor form. So it's very important to specify that temperature. So they're being kind of politically correct by giving us the temperature, which we never use in a calculation. So the partial pressure of the solution is 467 millimeters of mercury. And that's how we do Raoult's law for a non-volatile solute. Now, as we get into volatile solutes or mixtures, liquid-liquid, we have what we call ideal solutions and non-ideal solution. In an ideal solution, the vapor pressure is effectively a weighted sum. So we weight them by their mole fractions. So that's the mole fraction of part A times its partial pressure, mole fraction of B times its partial pressure, and you would see that the total of the solution is a sum of those weighted by their mole fractions. And you do need to do that calculation. Now, conceptually, you should also know this, that we can have a positive deviation and there's more vapor pressure. You can almost think of it as the liquids fighting to get away from each other into the vapor. And what we find is that the solution intermolecular forces are not very strong relative to the pure. So we would have an endothermic dissolving process. The molecules aren't very attractive to one another, so they'd be pushing each other out into the vapor, and we'd have more vapor in our solution. And we can have a negative deviation. This is for an exothermic, and this time it's the solution intermolecular forces that are stronger. So they like being together, so they keep pulling each other down into the liquid phase, out of the vapor pressure phase, so the pressure is lower. It's negative relative to this, which would be the ideal. Okay? So that's the theory behind it. You should understand what an ideal solution is, that the intermolecular interactions are effectively equal, pure relative to being in the liquid. So there are intermolecular forces, but they're equal. And then we have a positive deviation in which the pure is greater than the solution, and a negative deviation in which the solution is greater. The only calculation you're going to have to do is with an ideal. So in this case, we are given the vapor pressure of a solution. And the question is this an ideal solution? So what we need to do is calculate the pressure of the solution, assuming it's ideal. And if it's less than this, we have a negative deviation. If it's greater than this, we would have a positive deviation. Well, actually, if this is less than the ideal, it's a negative. If this is greater than the ideal, it's a positive. Okay, so that's going to mean I need my mole fraction of acetone. We've seen this a number of times. It's ethanone. It's a ketone. It's propanone. Forgive me for that. Propanone, it's a ketone. Prop is 3 carbons. Ketones have a double bond in the center, and then there'd be 6 hydrogens. There'd be hydrogens off each of the carbons. Times the partial pressure of the acetone plus my mole fraction of my chloroform, CHCl3, times my partial pressure of my chloroform. Okay. Now, I'm assuming that you can go moles to mass. I got for moles of acetone. You want to double check your math on this. I got 0.1 mole for the acetone. My moles for my CHCl3, I got almost 0.1, 0.997. So it's pretty much a 50 mole mixture. I went ahead and carried it out. My mole fraction of my acetone will be my acetone moles over the sum. And I get 0.5008. And if I do the same thing for my chloroform, or just subtract from 1, I get 0.4992. Okay, that's for my chloroform. So now my pressure of my solution is my mole fraction of acetone, 0.5008. And remember, this is ideal, times my acetone, which is 345, plus my mole fraction. So it's kind of a weighted average based on mole fraction, or a weighted sum might be a better way to say that. Okay, and my ideal is 319 torr. So that's pretty far off. So the answer to the question, is this an ideal solution, is a big fat no. And since my ideal, so my pressure of my solution is greater than the pressure ideal, I must have a negative deviation, which means that my intermolecular forces involved in this solution are greater than what those intermolecular forces were as pure substances. So that's how we would do Raoult's law. Now, there's just a couple other topics. There's one more quick thing to clean up, and I'm going to go ahead and do it in this video so we don't have to do another video, and that is osmotic pressure. Now, osmotic pressure is something that you might see especially in biochemistry. I used to do this. We used to purify things by dialysis. We'd use dialysis bags that would either allow water through or allow the solute through. In this case, we have a situation where we have a U-tube with a semi-permeable membrane. This membrane allows water to cross. So water can cross through it, but the solute cannot cross through it. And what's going to happen over time is that the water moves from a low solute concentration, which is, it's pure, not much solute there, to high solute concentration. And as the water moves across, the liquid levels become uneven. Now, the pressure that would have to be exerted in order to get those levels back is called the osmotic pressure. So if we pushed back on this, we would force the water to go back through to get our levels equal again. And osmotic pressure is given the symbol pi, I think usually a capital pi there. And this is molarity. Now, I have here R equal to this, but really that this is for atmospheres. R has to match the pressure units that are discussed in the question. So R must match our pressure. So let's take a look at this. We have beta carotene. It's one of the A vitamins, right? You're supposed to eat that for your eyes. It's supposed to be good for your eyes. We're going to determine its molar mass. And we're going to do this by using the osmotic pressure formula. Now, osmotic pressure is molarity, but I'm going to do the Fuller expression because I'm after molar mass. Moles are mass over molar mass, divided by liters of solution, times R times T, and yes, you better embrace Kelvin on this one. So I have 26.57, it's millimeters of mercury. Those are in milligrams, so I'm going to convert those to grams. Over my molar mass, which is my unknown, 10 milliliters of solution, I'm going to convert that to liters of solution. Now, since this was in torr, or millimeter mercury, I'm going to use 62.4. I almost converted when I did this, and then I thought there was really no reason to. We have this R value, we might as well use it. And then it's times 298 Kelvin. And if you solve for this molar mass, it's 537 grams per mole. And I did look that up, and according to Wikipedia, that is indeed the molar mass of beta carotene. All right, the rest of this unit is going to be a number of AP questions. I'm going to do as many as I have time and energy for. I actually have 10 of them planned. We'll see how that goes. And so until I see you in class or you hear me on the next video, this is signing off.